So one final example of us being able to utilize these closed forms to be able to take a recursive sequence and write it into the closed form. So we have e sub k is equal to 5e sub k minus 1 minus 3. And the first term in the sequence is going to be 2. So method of iteration. First iteration, the initial value is 2. E1, 5 times 2 minus 3. And we're going to leave it like that. We're not going to go through and compute that to be 7. E2, 5 times 2 minus 3. Okay, or we could write that as 5 square, and then we have another minus 3 in there, excuse me. So 5 square times 2 minus 5 times 3 minus 3. Okay, if we were to think about it like that. E3, 5 times the previous iteration, so that's 5 square times 2 minus 5 times 3 minus 3 minus another 3. Okay, and again, if we were to FOIL that out, or expand that, 5 cubed times 2 minus 5 squared times 3 minus 5 times 3 minus 3. E4, 5 times the previous iteration, 5 cubed times 2 minus 5 squared times 3 minus 5 times 3 minus 3 minus 3. Or, if we were to expand that, 5 to the 4th times 2 minus 5 cubed times 3 minus 5 squared times 3 minus 5 times 3 minus 3. And let's just do one more iteration. So that's going to be e to the 5th, or e sub 5, excuse me, is going to be 5 times all of that mess that we just had. So 5 to the 4th times 2 minus 5 cubed times 3 minus 5 squared times 3 minus 5 times 3 minus 3 minus 3. Okay, or another way to write that, 5 to the 5th times 2 minus 5 to the 4th times 3 minus 5 cubed times 3 minus 5 squared times 3 minus 5 times 3 minus 3. Now remember in the previous example, what we did was we left the first term alone because we noticed that the index and the exponent matched up very nicely. We also noticed that the index is one more than the exponent of all the terms that have, or the greatest term that has a factor of -3 within it. So it might be beneficial for us to factor out that -3 and rewrite this as 5 to the 5th times 2 minus 3 times the quantity of 5 to the 4th plus 5 cubed plus 5 square plus 5 plus 1. And then what we need to do is we need to figure out one of the closed forms that fits this pattern, this 5 to the 4th plus 5 cubed. And again, we see that this is the sum of the 5th powers. And so we look back at our closed forms, and I copied down a few of them, and we notice that this one matches up very nicely with that. So we have 1, 5, 5 square, 5 cubed, 5 to the 4th, except instead of n plus 1, we're going to have n plus 1 minus 1 because it's just a little bit less, or it's 1 less than what we need. So I'm going to get rid of that. In fact, I'm just going to hold on to this one. So that way we can see what we're doing, what's being substituted. Okay, so this is going to replace all this mess. Okay, so we're just going to substitute all of that. And so if I was to guess a closed form, okay, and we're going to simplify it after we're done, we could say that this is going to be e sub n is going to be equal to 5 to the n times 2. All right, because notice that each time the index matches up to the highest exponent, and then instead of all of this mess with the 5 to the 4th, etc., we have the coefficient of -3. That's going to be 5 to the n plus 1 minus 1, because we're 1 less than that, minus that index, and then 5 to the n plus 1 minus 1 over 4. We can simplify this algebraically, and we're going to. So that's going to be equal to 5 to the n times 2 minus 3/4 5 to the n. Okay, so distributing that through, and then plus 3/4, distributing -3 to -1, dividing by 4. Finally, we can simplify by combining like terms. So we're going to say 2 minus 3/4, and that should give us 5/4 times 5 to the n. All right, so that's going to be 8/4 minus 3, which should be 5/4, plus 3/4. Okay. What's really cool about this one is that we just happen to have the same bases of 5, so we have 5 to the first times 5 to the n. So another way that we could write this, if we chose to, and we do choose to, I'm going to go to a new, another way we could write this would be 5 to the n plus 1 over 4 plus 3/4. Okay. Or if we factor out the 1/4, 5 to the n plus 1 plus 3. Right. Now we need some initial conditions. All right. And of course we want the first term to be equal to the first term of what we started with. So we need to make sure whatever value we pick for n, we get 2 for the first term. And I think we plug in a 0 here. I think that's going to give us what we need as a 2, because that would give us 5 plus 3, which is 8. 8 over 4 is 2. So we're going to say n is greater than or equal to 0, and n is an integer. Okay, so pretty cool example of being able to utilize those closed forms that we used earlier in the course, and to be able to verify one of these sorts of recurrence relations, being able to take that and turning it into a closed form. And by the way, this should be equal to e sub n, not e to the n, but e sub n, because it is a sequence. So sorry about that. Let me squeeze that in there really quickly. All right, so hope this helps. This should enable you guys to be able to complete assignment number 11.